Lesson 17, Demo. Today we discover formulas for the derivatives of exponential functions and use them with other derivative rules to solve optimization problems. Number 1, can we apply the power rule to find the derivative of e to the x? That is to say, is the correct answer here bring the power down, copy the e, subtract 1 from the power, and no, that is not the right answer. We can't do that. Our power rule applies to x to a constant number, not a constant number to the x. This is just an entirely different creature. And number 2, recall from the group activities last class, we conjectured a formula for the derivative of f of x equals e to the x based on the graph shown below. So this is what you have on your page. This other stuff here, I just took a screenshot from the activity, from my work in that activity from last class. And what we did is we looked at 4 points on the graph of e to the x. And we drew some tangent lines at those points, and then we estimated the slopes of those things. And then we sketched over here the corresponding points that were on the derivative, using those slopes as the y coordinates. And then we connected the dots with some reasonable curve. And then we're trying to make a guess as to what the derivative of e to the x is. What is the function, the formula for this derivative curve? And so I'm guessing some of us made a good guess last class in this activity. We'll just show you a sketchpad thing real quick. The red curve is y equals e to the x. This is the tangent line at a particular point right now. X is roughly 0, and the y coordinate here is 1. And if you take a look at the slope of this tangent line, it sure looks like it's 1. If I move over to x equals 1, you can see here that's pretty close to 1. The y coordinate at that point, this y coordinate here, is 2.718 and change. It's e to the first. And the slope of this line happens to be 2.7180 and change, happens to match. And if we move to x equals 2, of course, the y coordinate gets bigger. We're up here now, around 7.4. And the slope gets bigger because this line is steeper. And you can see that the slope here matches the y coordinate. And if I go over to x equals -1, still works. Y coordinate is this, and the slope is this. And so it turns out in number 4, this surprising fact is true. You can read the proof in the book later on. But the derivative of e to the x is simply e to the x. It is just a copy of the y coordinate. It is ridiculous, but it is true. Using the chain rule then, we can take the derivative of e to the stuff. So if e to the x becomes e to the stuff, if the derivative of e to the x is e to the x, then the derivative of e to the stuff should be e to the stuff, but then the chain rule says times the derivative of stuff. Okay, this is the easiest derivative rule ever. It's not too hard to differentiate any exponential function. Here we're trying to take a derivative of a to the x, where a is just any old number, not the specific number that is e. And it turns out that a to the x becomes a to the x, which looks an awful lot like the e to the x rule, but you got to pay for it. You got to multiply that a to the x by ln of a. Again, a is that base. And so we can therefore use the chain rule to take a derivative of a to the stuff. It is a to the stuff times ln of a. That's the basic a to the x rule. But then chain rule says times the derivative of the stuff. So let's use these two new rules in these next couple of examples. Okay, so derivative of 5 to the x. So this is a to the x, where a is 5. So the derivative here is 5 to the x times ln of 5. That's it. Okay, let's try B. It says find the derivative of this more complicated function. So first, fundamentally, I have to figure out which rule we're applying in the beginning. This is a product of two functions of x. Therefore, we use the product rule. First, that gets copied, times the derivative of the second. Okay, 2 to the e to the x. So that is like an a to the x. In fact, it is an a to the stuff, where a is 2. So I'll use my a to the stuff rule. So we got times a to the stuff becomes a to the stuff. So 2 to the e to the x times ln of 2. That's the a to the stuff rule. But then times the derivative of the stuff. And the stuff I will circle here in orange. That's the stuff. Its derivative goes right here. And the derivative of e to the x is easy. It is just e to the x. Okay, that is half of the product rule. Now we continue the product rule and say plus the second. So we copy the second part, 2 to the e to the x times the derivative of the first. So the first is now this thing, e to the 4x squared minus 7x. That is an e to the stuff. And we just saw that the derivative of e to the stuff is e to the stuff. So we copy that stuff one time, times the derivative of the stuff. And the stuff is this. Its derivative goes right in here. And so the derivative of that stuff is 8x minus 7. So that's our answer there. Common algebra stuff that you can do with product rule is try to factor out the greatest common factor of the two terms separated by that plus sign. You'll see that these two terms have a lot in common. They both have an e to the 4x squared minus 7x, so you could factor that out of both. They both have a 2, you know what, maybe we'll actually do this one. I know typically we don't simplify, but this is a common technique that I want us to know. So we're looking for the greatest common factor. So e to the 4x squared minus 7x is there, and so we're going to factor that out of both terms. E to the 4, whoa, goodness. Let's try that again. E to the 4x squared minus 7x times, what else do they have in common, these two terms? I see a 2e to the x, and I see a 2e to the x, so that comes out as well. 2 to the e to the x. Okay, good there. And I don't see anything else that they have in common, so let's now write down what remains in each of the two terms. So in the top term, the top row, I see an ln of 2, and I see an e to the x. And then there's a plus sign, and then in the bottom row, I see just the thing in the parentheses. I'll leave it in the parentheses, although it's unnecessary here. And so this is our simplified form, factored completely, and this is going to be helpful when we have to set derivatives like this equal to 0, is to factor out the greatest common factor first. One last thing that we'll point out here is that the a to the x rule, remember we had these two rules now, e to the x and a to the x. The a to the x rule actually generalizes the e to the x rule. So in theory, you don't ever need to use this one right here. If you tried to apply the a to the x rule to e to the x, so in this case, the base that is called a is actually the number e. So according to our a to the x rule, the derivative of this is a to the x, which is e to the x, times ln of a. And a in this case, again, is e. And ln of e is a nice number. It's just 1. And so this is really e to the x times 1, or simply e to the x, which of course agrees with what we conjectured for this derivative last class. Of course, I'm not suggesting you don't bother memorizing that the derivative of e to the x is e to the x, but I just want to point out these two rules don't conflict with each other. This one generalizes that one.